So I'm going to bring you from the scale of big country like New Zealand to scale of a tiny, tiny droplet on like a surface. Um, so basically for those who don't know what I'm doing, for the last like 4 or 5 years, we were trying to develop so-called wetting gradients. These are surfaces where wetting properties are changing when we go along the surface. And just like one of the biggest metrics is the strength of such a gradient. It's basically how quickly we change these wetting properties. And if we push like hard enough our gradient, it will react and push hard enough our droplet. So we can even cause uphill motion on a single droplet. And that's how I spent like the last many, many years. But the question is like, okay, where is the vibration in all of this? Not yet. The vibration comes from a slightly different direction. If we think about energy generation or energy transformation, we usually think about power plants. We usually think about heat exchangers or some other elements of these systems. And we have two major sources of vibration. The first one, the machinery itself. We have pumps, we have I don't know, spinning shafts, turbines, etc., etc., etc. All of this, even if we don't want it, it will still generate certain level of vibrations. And there are studies that basically put it as a problem and try to see, do we need to dampen somehow this vibration? Do we need to isolate different parts of the system from each other? The second part, the second source of vibration is the flow stream itself. So when a fluid passes through a pipe or along a wall or something else, inevitably there will be some shaking. Obviously, sometimes we can't even feel it, but we can measure it. And there are a lot of modeling and other experimental investigations showing that it's actually a thing. And you can even see like a pipe doing like breakdowns when you actually push it hard enough. Anyway, so many other papers trying to put vibration as the problem that we need to solve. But recently, about like 5 years ago, some scientists started to think, what if we try to harness this vibration? So what if vibration is not the problem, but a solution? And then the hype train basically departed. So many papers. We can try to even attach our heat exchanger to something and shake it, and it will improve the heat efficiency, or prevent falling, or do some other crazy things. Well, all of this is great. The only problem was it was tested on a big system right away. So people took like full heat exchanger and started shaking it, and then it's like, oh wow, we saw like 3% increase in the heat transfer coefficient or something. Fantastic, but as a fundamental physicist, to me it's always a question like, okay, why? Why do you see what you see? So we didn't come up with anything better than basically take a small laboratory shaker, put a camera around, put some light, and basically just shake the droplet. Oh, we're glitching a little bit. Anyway, you got the idea. So basically, looking at a single droplet, applying vibration in different directions, vertical, horizontal, different amplitudes, different frequencies, we started to map and study how a single droplet responds to this. If we talk about just a standard like metal surface, nothing interesting is going on. You just saw the video. The droplet just stays and just kind of wobbles. If we put a superhydrophobic coating, things become a bit more interesting, but still not there yet. Why? Because if we talk about vertical vibration, the droplet is just jumping and not going anywhere. If we talk about horizontal vibration, the surface is literally just sliding under the droplet. There is not enough friction to cause any reasonable motion. So it's kind of, again, cool, but so what? How we can use it? And that's finally where our wetting gradients step into the picture, because if we put a gradient and start shaking. In case of vertical vibration, yeah, the droplet is jumping, but it's always going a little bit to the side, a little bit to the side, a little bit to the side, and finally going away. For the horizontal vibration, it's even more fascinating. Our surface starts moving, pick up the droplet on one side of the gradient, and throws to another side of the gradient. Fantastic. So as I mentioned before, we just started mapping. We started seeing kind of what we can achieve with this. I hope it wasn't glitching that bad. Still, you got the idea, I hope. So yeah, we just started mapping, and that's what we came up with. So the black curve is standard metal hydrophilic surfaces when the droplet is just stuck to the surface, not moving anywhere. The pink line is different superhydrophobic surfaces with just like commercial coating. So yeah, kind of as I mentioned before, we have sort of a response on vibration from the droplet, but unfortunately it's not moving anywhere. And our wetting gradients, they are kind of in between. So yes, you need a little bit more vibration to initiate some motion, but at least we are now skyrocketing the droplets from like one position to another, and we achieved motion for like 6-8 millimeters. Doesn't sound that much, but for a scale of a tiny droplet, 8 millimeters is like on the other side of the room. And this is for like horizontal vibration. If we talk about vertical vibration, that's when the gradient started to shine. Black and pink line, the same. All other different colors, it's just the different strengths of the gradient. So at the beginning I mentioned that's how quickly we change wetting properties. So for some combinations of frequencies and amplitudes, we can see that wetting gradients, they outperform even commercial coatings, meaning that we initiate droplet motion even earlier than it's happening on a like standard superhydrophobic surface. So we was like, cool, we should probably write a paper about it. So we wrap it up, put some physics in it, explain some different things, submit it, and we got editor's pick. Editors wrote us that the contribution to the field was that fantastic that it deserves something. I was like, whoa, but here it could be like a reasonable question. Cool, we are at the energy symposium. Where is the energy in all of this? The energy came actually through the discussion with one of the reviewers. So one of the reviewers was just like, well, theoretically speaking, you can actually calculate the energy output of the condensation event for a single droplet. So if we kind of just like in a very crude form, scale it up to like hundreds or thousands of droplets, you can theoretically estimate what's the kind of power saving or power output of the condensing heat exchanger you can achieve at a certain like shedding rate, let's say. And I was like, well, cool, let's do that in this case. So we requested some support from Otago Energy Research Center. We got a seed grant, and instead of having a small shaker that shakes a single droplet, we bought this big shaker that is going to shake a full heat exchanger that will be put in the test rig. So we can basically do the same thing that we did for the droplet. We can start mapping. We can start seeing what's exactly happening at what frequencies, what amplitudes, and we already have the picture of a single droplet. And now we're kind of linking it to the bigger picture of the whole heat exchanger. It kind of sounds similar to what previous papers did, but again, they didn't look at a single droplet. They didn't explain it from a perspective of a single droplet. We did. To wrap it up, basically, we demonstrated that the even low-level vibration could be utilized to enhance the droplet shedding, depending on direction, frequency, depending on the amplitude. And yes, hydrophobic surfaces, they do help with the shedding rate, but as I mentioned, for some combinations on frequencies and amplitudes, some wetting gradients can outperform it, which is again even better. And we demonstrated how fundamental findings could actually lead to potential applications in the like real technology and the real environment. And hopefully we're going to test it, as I mentioned. Thank you very much.
Great, thank you. Any questions?
Oh, here we go.
No, I'm very interested in whether you are also harnessing gravity to help you with shifting your droplets.
That's what I intentionally kind of hid under the table. So indeed, if we look into a real heat exchanger, you don't really expect a perfectly aligned surface. So definitely for a vertical wall, especially superhydrophobic vertical wall, you may expect that the gravity, or if you especially align the flow stream with it, it will help like dramatically. But that's where we step into like another side of my postdoc project. Another problem is that the droplet is in the confined space. So it will behave slightly differently to what we consider open surface. So the problem of any heat exchanger is that even a small droplet is usually bridging between two different plates and usually gets stuck. And that's sometimes how wetting gradients, as a part of my another talk, spoiler, that's how wetting gradients could help. We kind of break this asymmetry, so we distort the droplet shape, twist it a little bit, and then the gravity or the flow or something could pick up the droplet and finally allow it to departure from this area, let's say. So in short, yes, gravity will help, but now we're stepping into constructive nuances.
Great. Any other questions? In which case, oh, yes, hang on.
Does it have applications in other contexts, like, shedding droplets off vehicle windows for safety and things like that? Or is it like not transparent, so you can't use it on glass, stuff like that?
So yeah, I kind of skipped most part of the manufacturing. So for the manufacturing, we do laser ablation. So we literally create a microstructure. I will pull out quickly the photo. We create a microstructure on the surface. And with metals, it works perfectly because we don't care about their transparency. With glass, it becomes a bit more tricky because, yes, it indeed changes the transparency, and especially the denser the structure is, the less transparency we have. So we working in this direction a little bit because for the solar panels, it's basically a way to create like self-cleaning surfaces, etc., etc., etc. But again, there are too many technical nuances in this case. So it's possible, yes, it's applicable potentially. Now the big question, how actually we can do that. But speaking a bit broader, in terms of application, anywhere where you don't want droplets to accumulate, you can basically apply it. So one of the potential thing that we mention periodically is wind turbines as well, especially the offshore ones. When condensation starts to appear, especially at cold nights, so to avoid freezing, you want the droplets to departure from the surface. And that's the problem when you work with the condensate. You may not have wind. The surface may be aligned in the direction you don't want it to be, etc., etc., etc. So something that passively can direct droplets out of this area is usually preferable.